All right, I have a couple more examples of how we can use the continuous time Fourier series properties to find the Fourier series coefficients of continuous time periodic signals. So let's recall first of all that we found the Fourier series coefficients of a square wave centered, or an even square wave centered at the origin with pulse width 2t1 in period t. And those Fourier series coefficients were given by this thing here. Let's call that x of t, and its Fourier series coefficients ak. So just recall that. We're going to need that at the end of this video, kind of as a surprise. So this is a little foreshadowing, if you will. And the question at hand here, now at the left, is find the Fourier series coefficients of the impulse train, shown below. Choo-choo, impulse train. So an impulse train is an impulse at the origin. Remember that an impulse does not equal 1. It's a spike to infinity, and it just integrates to 1. So an impulse train is a spike at the origin, and then a spike at t, and 2t, and 3t, and 4t, and also at minus t and minus 2t, and so on. So this is periodic. It goes on forever, and it has these spikes at regularly spaced intervals spaced by t. So it's periodic with period t. All right, let's find its Fourier series coefficients. Now, at the beginning of this, we are not going to use any properties. We're just going to calculate it by hand. Okay, so we'll say that ak is 1 over t times the integral over a period t of wt, right? I'm calling this w because we used x over here. So we're going to say wt e to the minus j k omega 0 t dt, right? That's the Fourier series definition, analysis equation. Now, I can pick any interval I want to integrate. I'm not going to pick from 0 to t. I'm not going to go from, I'll draw it in orange, I'm not going to integrate from 0 to t. I can pick any interval so long as it's got that same width of a period. And I'm not going to go from 0 to t. Why not? Because it's ambiguous. It's ambiguous. In this interval 0 to t, does this impulse fall in that interval? Does this impulse fall in that interval? It's ambiguous. So instead, I'm just going to go from about negative t over 2 in red to t over 2. Now it's much clearer. So I'm going to pick my interval strategically. Minus t over 2 to t over 2. And in the red interval, it's clear that there's just one impulse, right? So the signal is wt. Wt is just the impulse. E to the minus j k omega 0 t dt, right? Okay, and now from the sifting property of the impulse, this integral is simply equal to 1. And so I get 1 over t. So ak is just constant, 1 over t. Now, if you don't remember the sifting property, go back and check out the sifting property. This is why I make the videos so short, so that you can find the exact subject you're looking for from the sifting property. So in this case, you'd want to check out the continuous time impulse. Its property, one of its important properties, is the sifting property. Anyway, so we have the Fourier series coefficients now of this impulse train. They're very interesting to us. They're just constant. 1 over t, 1 over t, 1 over t. That is the Fourier series coefficient. Okay, now moving along. So we didn't use any properties there, any of the continuous time Fourier series properties. Now we're going to try to relate y of t to w of t. And let me be a little bit more clear here. Instead of ak's, since we used ak's over here for x of t, I'm going to just change these to bk's. You can call them whatever you want, right? So I'm going to call them bk's, and now we're going to try to find the Fourier series coefficients of y of t. We're going to call those ck's, because we used a, we used b. Now we're going to find ck's. So the question right now is y of t related to w of t? And if so, how? So we see, yeah, it is. Y of t is equal to, well, if I take wt and if I shift it to the left by t1, so if I do this, okay, then I have the positive spikes occurring at, at minus t1 and at t1 and so on. So I've got this guy. That's partially what I want. And then I need the negative spike. So I'm going to take w, subtract it, okay, for the negatives, and I'm going to shift that to the right by t1. You see? So again, if I take w and if I shift it to the right by t1 and then I negate it, now I have the negative impulses. And if I add that to w shifted to the left by t1, then I have exactly y. Okay, so here's the relationship between y and w. So we've just calculated the Fourier series coefficients of w. Now can we use properties, being that we have a relationship between the two, to calculate the ck's? Okay, so I need the linearity property. The linearity property allows me to consider each of these terms separately, w of t plus t1 and w of t minus t1. So I'll just write piece by piece. Okay, and then when I consider each one separately, I'm going to need the time shift property because each one is a time shift. Okay, so let me take the Fourier series operation of this equation. And so on the left, the Fourier series of y of t we're calling ck, that's what I want. And so what's the Fourier series of the first term? Well, the time shift property says I need e to the positive jk omega 0 t1, right? Because this time shift here, let me write out the property. The property says w of t minus t0 has a Fourier series e to the minus jk omega 0 t0 times bk, right? So we compare what we have to the formula, and we see that t1 is minus t0, right? T1 is minus t0. So we put, for minus t0, we put a t1 in, and so that we get this, times the Fourier series coefficients of w, which were what we were calling the bk's. So again, this is the time shift property. Okay, and then the next piece we have minus. Now we've got some symmetry happening, so I can compare this to my formula, and we just see that t0 is t1. So this becomes minus jk omega 0 t1. Notice I have a negative there because the negative in the formula. Here it was positive because of this. I was actually negating a t1 times the bk's. Okay, so what can I do with this? Well, I can factor out the bk's, and I've got e to the jk omega 0 t1 minus e to the minus jk omega 0 t1. Okay, now if you are very observant, you might see that there is a sinusoid happening here. If I take this and I divide it by j2, of course then I need to multiply by j2, then inside the parentheses is a sine wave. So now I have the ck's that I'm looking for are j2 times the sine of k omega 0 t1, and so times bk, and the bk's are constant at 1 over t. And there's my answer. Those are the Fourier series coefficients of this guy here, y of t. Now, let's continue, and I'm going to delete the impulse train, this first one. So feel free to pause the video if you need to. Okay, but I need the work that we just did. Now, is there a relationship between y and x? Is there a relationship between those two guys? Well, there is. Notice that the derivative of the square x of t is equal to y of t. Remember, the derivative is the slope. So let's consider this. If on the pieces that I have 0, right, it's constant and I have 0 slope, then I go from 0 to 1 instantaneously. So I have a spike up to 1 in the derivative at t1, at minus t1. That's what I have here. And then I hang out at 1 for a while, and so I've got a constant, so I've got 0 slope. So it goes back to 0 after that spike. And then at t1, I go from 1 to 0 instantaneously, so I have a negative spike in the derivative, and that's exactly what I have here. And it repeats. So hopefully you understand from calculus that the derivative of this square is in fact y of t, these spikes. So now we can apply the differentiation property. The differentiation property, which I'll write here, it says, in the table it says jk omega 0 times ak is the Fourier transform, or excuse me, the Fourier series of the derivative. Okay, so let me take the Fourier series of this equation. So on the left-hand side, I will have jk omega 0, and then the Fourier series coefficients of x of t we're calling ak, equals the Fourier series coefficients of y of t, which we're calling ck. And notice if I can get back, actually, the ak's, the work that we have already done. If I take my ck's and I divide by jk omega 0, let's see what happens. So I've got my ck's here. If I divide by j, then you'll notice the j's cancel. So I've got 2 sine of k omega 0 t1 divided by k omega 0 t. Okay, and then remember that omega 0 is 2 pi over t, and so omega 0 times t is just 2 pi, and the 2's cancel, and so I'm left with ak is equal to sine of k omega 0 t1 over pi k. And so we divided by k here, so this does not hold for k equals 0, but for k not equals 0, this should hold. And voila, look at what we have. We got back our original work, but we did it in a completely different way now, starting with the impulse train and using properties of continuous time Fourier series. Amazing!